For over 200 million years, the ocean had apex predators, and not one of them was a shark. Not in the Cambrian seas, where life first invented the concept of a chase. Not in the Ordovician, when creatures the length of city buses patrolled the water column. Not in the Silurian, when the largest arthropods that ever lived ruled the shallows with armored claws and compound eyes. Not once, through dynasties that lasted tens of millions of years, through extinctions that reshaped the entire planet, did a shark sit at the top. And yet today, we think of the shark as the ocean's permanent, inevitable ruler. The shape evolution was always building toward. The final answer to the question of what a perfect predator looks like. What took so long? What filled that throne before the shark arrived? And what happened to every creature that held it? Creatures that, in their time, were every bit as dominant, as ancient, as seemingly indestructible as the shark appears to us now. In this video, we will answer these questions. And if these kinds of deep ocean mysteries interest you, subscribing helps this channel a lot. Every video here is built from hours of research, and your support is what makes the next one possible. In 1946, the Australian government sent a geologist named Reg Sprigg to inspect some abandoned silver mines in the Ediacara Hills of South Australia. He expected rock. What he found, pressed into the ancient sandstone of a hillside, were the outlines of creatures. Flat, silent impressions, as if the seafloor itself had been used as a mold for something soft, something boneless, something that left no other record of its existence, except its shape. Sprigg recognized he was looking at fossils. What he didn't immediately understand was how old they were. These were the oldest complex animals ever found, not 65 million years old, like the last non-avian dinosaurs, not 250 million years, like the earliest mammals. These organisms lived between 635 and 541 million years ago, in a geological period now named, in honor of that South Australian hillside, the Ediacaran, a time so remote that the continents themselves looked nothing like they do today, arranged instead into a supercontinent called Panatuia, centered near the South Pole. The creatures Sprigg found were unlike anything he had seen, and that, it turns out, is almost literally true. One of them, Dickinsonia, was an oval ribbed organism that could grow over 1.5 meters in length, the size of a large coffee table. It had no eyes, no mouth, no clear head or tail, no obvious organs. It likely absorbed nutrients directly from the microbial mat it lay upon, the way a living shadow might simply dissolve into whatever it rested on. Beside it, Trabrachidium, a disc-shaped animal with 3 arms spiraling outward from its center, like a pinwheel frozen in stone. Immobile, a filter feeder, probably, or a suspension feeder, simply waiting for the ocean to deliver something worth taking. Nearby, Kimberella, a slug-like creature that seems to have grazed actively, leaving scratch marks in the sediment that resemble the feeding traces of modern snails. And Charnia, a frond-shaped organism thought to have lived in deep water in complete darkness, anchored to the seafloor like a feather planted in mud. Their precise relationship to modern animals is still debated. Their feeding strategies, their life cycles, much of their anatomy, genuinely unknown. What science can say with confidence is this: these were the world's first large, complex, multicellular animals, and the ecosystem they inhabited had no predators. That bears repeating. No predators. The Ediacaran seas were not peaceful because their inhabitants were particularly resilient or well defended. They were peaceful because the evolutionary idea of eating another animal had not yet been invented. Dickinsonia did not fear Trabrachidium. Kimberella did not flee from Charnia. Nothing hunted anything. The ocean floor was carpeted in microbial mats, ancient, bacterial, and the creatures of the Ediacaran fed upon them or upon the chemistry of the water itself in something close to genuine tranquility. It could not last, and the reason it could not last is almost ironic. Life itself ended it. As Ediacaran animals diversified, the ocean's chemistry changed. Oxygen levels rose. Bodies became more complex. Sensory systems appeared, rudimentary, then more refined. Something moved faster. Something else moved to avoid it. And around 541 million years ago, the world accelerated into an event that paleontologists call the Cambrian explosion, when most of the major animal body plans that still exist today appeared in the fossil record in what, geologically speaking, was an eye blink. The Ediacaran creatures, slow and sessile and unarmed, could not keep up. Most went extinct. A few persisted, perhaps, into the early Cambrian, but the world they had built, the quiet, predator-free ocean, was gone forever. Picture an ocean lit by shallow tropical sun. The water is warm and clear over a seafloor crowded with life. Trilobites armored like tiny tanks, soft-bodied worms, threading through the sediment, sponges rising in slow, permanent columns. The diversity is extraordinary, but above them, something is watching. It moves with undulating flaps along its sides, a large fan-shaped tail, driving it forward through the water column. Its eyes, two dark discs mounted on stalks, scan the sea below. And from just below those eyes, two segmented arms curve forward, lined with spines. Its mouth is circular, made from overlapping plates. It is perhaps the length of a human body from fingertip to fingertip. It is Anomalocaris canadensis. Its name means, in a rough translation from Greek and Latin, the abnormal shrimp. It is the world's first apex predator. The story of how we came to know this animal is itself a kind of parable about scientific knowledge. Anomalocaris fossils were first collected in 1886 by Richard McConnell of the Geological Survey of Canada, who climbed Mount Stephen in British Columbia looking for trilobites and found something he couldn't identify. 25 years later, its circular mouth was separately excavated and labeled a jellyfish. Its decomposed body was collected from another deposit and filed away as a sea cucumber. 3 fragments. 3 different phyla, one animal, unrecognized for nearly a century. It was not until the 1980s that these 3 body parts were found together in a single specimen and understood to be one creature. As Stephen Jay Gould, Forgever, who popularized the Cambrian explosion in his 1989 book Wonderful Life, described it, a tale of humor, error, struggle, frustration, and more error, culminating in an extraordinary resolution that brought together bits and pieces of 3 phyla in a single reconstructed creature, the largest and fiercest of Cambrian organisms. The eyes, when finally studied in detail, were astonishing. In 2011, fossilized specimens from the Emu Bay Shale of South Australia revealed that Anomalocaris possessed compound eyes with over 24,000 lenses, each rivaling the visual resolution of a modern dragonfly. Its vision was, in the context of the Cambrian Ocean, extraordinary, 30 times more powerful than the eyes of a trilobite. What did it do with that vision? Here, science pauses. For decades, the leading theory was that Anomalocaris used its spike-lined arms to seize trilobites and crush them with its circular, plate-lined mouth. Bite marks of matching shape were found on trilobite fossils, fossilized feces, so large that no other Cambrian animal could have produced them. Contained trilobite fragments, but a 2023 study, published in the Proceedings of the Royal Society B, complicated the picture. Biomechanical modeling of the appendages showed that grabbing hard-shelled prey would have caused significant damage to the arms themselves. The more likely interpretation, Anomalocaris was a fast, agile, open-water hunter of soft-bodied prey, a speed predator rather than a crusher. These were the orcas, said paleontologist Jakob Winther of the University of Bristol, the great whites of the time, specialists even at the dawn of predation. The arms race was already that sophisticated. What Anomalocaris almost certainly did, regardless of exactly what it ate, was reshape everything around it. In response to a creature with those eyes, that speed, that capability, the Cambrian Ocean began to armor itself. Shells appeared, or thickened. Burrowing became common. The evolutionary dynamic of predator and prey. The evolutionary dynamic of predator and prey, the engine that would drive the next 500 million years of animal evolution, started here with this strange misidentified, many times misunderstood, animal in the warm, shallow seas of British Columbia. It ruled for perhaps 20 million years. Then the Cambrian gave way to the Ordovician, and the seas filled with something larger. The shell extends from the water column like a spear, straight, tapered, pale, and chambered. At its widest end, a crown of tentacles fans outward into the current. The animal itself occupies only the last and largest chamber, its body sealed from the rest of the shell by a series of walls it has spent years constructing, sealing, and abandoning as it grew. A tube, the siphuncle, runs the full length of the shell, threading through every chamber, allowing the animal to pump fluid in or out, adjusting its buoyancy with a precision that no fish of this era has yet achieved. The shell is 9 meters long. Camarocera's chambered horn was a nautiloid cephalopod, an ancestor in its broad lineage of the modern squid, the octopus, the chambered nautilus. In the Ordovician seas, roughly 470 million years ago, nothing else was even close to its size. It was the largest animal that had ever lived, and it was almost certainly a predator. There is fossil evidence. A trilobite from the late Ordovician Lindsay Formation in Ontario bears a bite mark that matches, precisely, the beak of a nautiloid cephalopod. The trilobite was killed before it could molt again. The most likely culprit, Camaraosaurus, or something very like it. Specimens of the related genus Endocerus have been measured at 5.7 meters in shell length. One reported specimen was estimated at over 9 meters, though that particular fossil has since been lost and cannot be confirmed. It lives now only in description. Whether we should trust that description, science cannot say with certainty. What it can say is this: in some localities in Scandinavia and Morocco, the fossils of these great straight-shelled nautiloids accumulated in such quantities that they formed the rock itself, entire limestone formations composed almost entirely of nautiloid shells, stacked and compressed over millions of years. They were so numerous, so dominant, that the sediment of the ancient seafloor is made, in places, from their remains. You can buy a polished slice of Moroccan Ordovician limestone at a market stall today and hold in your hand a cross-section of Camaraosaurus, extinct for 450 million years, its internal chamber still visible as geometric rings of brown and cream. Consider what that means. Those limestone beds stretch for kilometers. They represent millions of individuals. The nautiloids were not merely apex predators. They were, in some sense, an ecological foundation, without many vertebrates to compete with them. They ruled the open water of the Ordovician seas. Trilobites, jawless fish, early arthropods, all potentially prey. Then, around 443 million years ago, a mass extinction struck. Gondwana, the ancient southern supercontinent, drifted over the South Pole. Glaciers formed, sea levels fell, draining the shallow continental shelves where life was most concentrated. In the extinction that followed, Somewhere between 60 and 85% of all marine species disappeared. The great nautiloids were among the hardest hit. They never recovered their former size or dominance. The throne they had occupied for 30 million years went vacant. For a while, when the seas refilled after the Ordovician extinction, they refilled with a different world. The nautiloids persisted, diminished. New kinds of fish appeared, still jawless, still small, but beginning to diversify. And in the shallow coastal waters, in the brackish estuaries and lagoons, something extraordinary was evolving. Not a fish, not a cephalopod, an arthropod. In 1818, a fossil collector named S.L. Mitchell found a strange fragment in the rocks of New York State and initially thought it was part of an ancient catfish. It was reclassified 7 years later by zoologist James Ellsworth, Decay, who recognized it as an arthropod, though unlike any arthropod alive. 6 jointed legs, a heavily segmented body, a long tail ending, in some species, in a flat paddle that functioned as a rudder. At the front, 2 claws, not for walking, but for seizing. The eyes set wide apart, providing depth perception. The state of New York would eventually designate this creature, Eurypterus remipes, as its official state fossil, a distinction it shares with no known living relative. The Eurypterids, sea scorpions. With approximately 250 known species spread across more than 200 million years of geological time, they were one of evolution's more sustained experiments. The smallest fit in the palm of your hand, the largest Jaekelopterus rainii, known from early Devonian deposits in Germany, is estimated to have reached 2.3 to 2.6 meters in length, based on fossilized claws alone. It was the largest arthropod that ever lived. Longer than a Komodo dragon, roughly the weight of a large adult human. The Yale Peabody Museum holds a single tergite, a single skeletal plate, from a Patriotid eurypter, called a Cutiramus macropalamus, collected from Passage Gulf, New York. 1 plate. Estimated, including extended claws, to have belonged to an animal larger than an adult human being. They were not simple. Their ecology ranged within those 250 species, from ambush predation to active pursuit. Some developed elongated limbs and broad paddles for swimming. Others became bottom walkers, heavily armored. The largest paterygotid forms possessed binocular vision, depth perception, which enabled them to judge distances in 3 dimensions, a capability essential for attacking prey, rather than simply waiting for it. They attacked the jawless fish that shared their habitat. In all probability, they were the reason those fish were so heavily armored. The ostracoderms, as science calls the armored, jawless fish of this period, bore bony head shields that encased their skulls in what amounted to helmets. As one paleontologist observed, that armor served as protection against the giant scorpion-like arthropods, the Eurypterids, which were dominant predators of the Cambrian, Ordovician, and Silurian periods. Later, when the Eurypterids finally disappeared, the descendants of the ostracoderms shed their heavy armor. It had become unnecessary. There is also evidence, not conclusive but growing, that some Eurypterids could briefly leave the water. Their book lungs and slit-like structures, found preserved in some specimens, resemble features found today only in terrestrial arachnids. They may have been capable of hauling themselves onto land, perhaps to migrate between water bodies, perhaps to breed in protected shallows. They predated the colonization of land by tetrapods by tens of millions of years. In the Silurian, the shore was still a new frontier, and even the sea scorpions were beginning to test it. They went extinct. Finally, at the Permian-Triassic boundary, 251.9 million years ago, in the most devastating mass extinction in Earth's history, the event that killed perhaps 90% of all marine species. By then, the sharks had already been swimming for over 150 million years. But even during the golden age of Eurypterids, the earliest sharks were small, marginal, poorly understood. The fossils are just scales, a fraction of a millimeter long. The Eurypterids had not noticed them. Running alongside these dynasties, the nautiloids, the sea scorpions, was another story. A quieter one, a story not of dominance, but of survival and of what it costs. In the Middle Ordovician, the first vertebrates appeared in the fossil record, not fish as we recognize them. No jaws, no paired fins, no lateral stability. Their heads were encased in solid, bony shields, not the elegant, streamlined armor of a modern fighter jet, but heavy, cumbersome, immovable helmets of bone that made them slow and prone to sinking. Some of the earliest forms looked, as one description has it, like tadpoles wearing stone hats. These were the ostracoderms, a name meaning, in Greek, shell-skinned. They were small, often less than 30 centimeters long. They fed by suction, drawing small organisms and organic particles into their permanently open mouths. They were, in most ecological senses, prey animals, armored against the Eurypterids and the nautiloids that hunted the same shallow seas, and yet they carry in their bodies the most important innovation in the history of vertebrate life. They were the first animals to use gills exclusively for breathing. Every previous chordate with gill structures used them for both feeding and respiration simultaneously. The ostracoderms separated these functions. Gills in their bodies became dedicated organs of oxygen exchange. The respiratory system we carry in our own chests is, in a direct evolutionary sense, their invention. They were also the first animals with a backbone. By the end of the Silurian, roughly 419 million years ago, ostracoderms outnumbered every other kind of fish in the sea. It was their peak. Something was changing in the ocean around them. The first jawed fish were appearing, and some ostracoderms grew larger in response, as if sensing the arms race accelerating. But the jaw, when it came, was a revolution they could not answer. The ostracoderms went extinct at the end of the Devonian. Their descendants did not. The lineage that began with those helmeted, jawless, bottom-dwelling filter feeders eventually produced the placoderms, the armored-jawed fish of the Devonian, then the bony fish, then the tetrapods, then the amphibians, the reptiles, the mammals, then, in an unbroken line of descent from those stone-helmeted Ordovician creatures, us. The ostracoderms were our ancestors. They lived in terror. They armored themselves against monsters. And in doing so, they built the body plan that would eventually inherit the Earth. Its skull alone is over 60 centimeters long. It has no teeth, at least not in any sense you would recognize. Where teeth would be, there are instead two plates of bone, upper and lower, hardened and self-sharpening, ground against each other over millions of years of use until they function as blades. They do not crush, they shear, and they move with a speed that is almost impossible to believe in something this large. From closed to fully open, 20 milliseconds. The whole feeding cycle, open, seize, close, takes between 50 and 60 milliseconds to complete, faster than the blink of a human eye. In that half second, in those jaws, the force generated at the blade edge exceeds 5,300 newtons. That is a bite rivaling, according to biomechanical models, the force exerted by a large alligator, or Tyrannosaurus rex. This is Dunkleosteus terrelli, named for David Dunkel, the paleontologist who first described its fossils, named, in part, for the Greek word for bone, osteus, because of the massive bony plates that form its head and thorax. It was a placoderm, one of the armored-jawed fishes that replaced the ostracoderms and came to dominate the Devonian seas. from roughly 415 to 360 million years ago. Mark Westneat, curator of fishes at the Field Museum, who co-authored a landmark 2007 biomechanical study of the skull, said this heavily armored fish was both fast during jaw opening and quite powerful during jaw closing. This is possible due to the unique engineering design of its skull and different muscles used for opening and closing, and it made this fish into one of the first true apex predators seen in the vertebrate fossil record. His co-author, Philip Anderson, was more direct. Dunkleosteus was able to devour anything in its environment. The exact size of Dunkleosteus tyrrelli remains genuinely uncertain. Estimates range from 3 to 8 meters in total length. The range is large because only the bony head and thoracic shield reliably fossilize, and the rest of the body, like a shark's, was mostly cartilage. It left almost nothing behind except its skull. We have the weapon. We are still reconstructing the animal around it. What we know, it was a pelagic predator, an open water hunter. It ate armored placoderms, early sharks, arthropods, ammonoids, anything that shared its ocean and was smaller than itself. The bladed jaws, capable of ripping apart prey larger than its own mouth, were a feature that sharks would not develop for another 100 million years. Let that land, the tool we associate most intimately with the shark. The ability to slice and shear through resistant prey was invented not by the shark, but by Dunkleosteus 100 million years earlier. The shark, in the late Devonian, was prey. Fossils of early sharks have been recovered from the same Cleveland shale formations that preserve Dunkleosteus tyrrelli, and some show marks consistent with having been bitten cleanly in two. And here is where the story turns on itself, because Dunkleosteus also reveals something unexpected about its own reproduction. Some placoderms, closely related to Dunkleosteus, have been found with evidence of internal fertilization. One specimen preserved what appears to have been an umbilical cord. These armored fish, the rulers of the Devonian seas, may have been among the first vertebrates to give birth to live young, nourishing offspring internally before releasing them into the world, a behavior we now associate most strongly with sharks. The animal that came before the shark was already, in some sense, practicing to become it. Then, 358 million years ago, the late Devonian extinction event arrived. It was not a single catastrophe, but a prolonged crisis, a series of pulses spread across perhaps 1 million years, during which ocean temperatures fluctuated, oxygen levels in the water dropped catastrophically, and marine ecosystems around the world collapsed. At least 75% of all species on Earth disappeared. Among them, every placoderm, every ostracoderm, the great nautiloids, already diminished, was struck again. The sea scorpions were reduced to a handful of marginal forms. The ocean that emerged from the Devonian extinction was largely empty. Cleared of its rulers, the throne, if you want to call it that, was vacant. And into that vacancy swam the sharks, not triumphant, not as conquerors, as survivors, small, flexible, eating what was available, filling niches that had been emptied by catastrophe. The Carboniferous period, which began 359 million years ago, is now called the Golden Age of Sharks. But that name is a little misleading. It was a golden age partly because almost everything else was gone. The sharks that diversified in the Carboniferous were bizarre and extraordinary by any measure. Stethocanthus with an anvil-shaped fin on its back, Helicoprion with a spiral buzzsaw jaw. One of the strangest dental structures in the history of vertebrate life, its teeth arranged in an inward coiling spiral that we still don't fully understand. Falcatus, in which the males bore a long spine curving forward over their heads, the purpose of which remains unclear. None of these were the sharks we know, the sleek, powerful, torpedo-shaped predator of modern oceans. The great white, the tiger shark, the oceanic whitetip, would not appear for another 100 million years. The first true sharks appeared around 395 to 400 million years ago, in the early to middle Devonian. We know this mostly from their scales. Tiny, a fraction of a millimeter long, the kind of fossil you'd miss if you weren't looking for it, as one scientist from the Australian Museum put it. The very first sharks are a mystery. All we know of them are these tiny little scales. We have no teeth, no body fossils. The creature we hold up as the ocean's eternal champion entered the fossil record as a whisper, and yet, sharks have now survived 5 mass extinctions. The asteroid that killed the non-avian dinosaurs 66 million years ago, sharks endured it. The Permian Triassic event, which destroyed 90% of all marine species, sharks endured that too, though barely. Their secret, one marine biologist suggested, is that they are not one thing, but many. Deep water sharks, shallow water sharks, sharks that filter plankton, sharks that ambush seals, sharks that scavenge carcasses on the abyssal plain. Their diversity is their resilience. They cannot all die at once because they are not all doing the same thing. But there is a word missing from that explanation. Throughout 450 million years of mass extinctions, of meteorite impacts, of glaciations, and volcanic winters, and the collapse and rebuilding of entire ecosystems, the shark survived. Today, for the first time in that history, survival is no longer guaranteed by geology. More than a third of shark species are now classified as threatened or near threatened with extinction, primarily due to overfishing and the demand for shark fin, the animal that outlasted Anomalocaris and Camarasaurus and Dunkleosteus, the creature that inherited an ocean vacated by 5 successive dynasties, cannot survive a single century of sustained industrial pressure. Every one of the creatures in this story believed, if we can speak of organisms believing anything, in the permanence of their world. The Eurypterids ruled for over 200 million years. If geological time were compressed into a single human year, that reign would last nearly 2 months. It felt, presumably, like it would last forever. It did not. Go back one more time to the Ediacaran, to the ocean floor of 560 million years ago, carpeted in its ancient bacterial mat, lit by filtered sunlight in the shallows. Dickinsonia lies there, flat and ribbed and still. It absorbs what the mat offers. It moves, perhaps, a few centimeters over the course of a day. It leaves when it moves, an impression in the sediment, a ghost of its presence, preserved in stone for 500 million years. It had no eyes. It could not see what was coming, the explosion of predation that would follow its kind's extinction, the dynasties that would rise and fall in the seas above the descendants of its contemporaries, the nautiloids, the sea scorpions, the armored kings, the shark. What it left behind is a shape in rock, a quiet record, a body pressed into stone so gently and preserved so faithfully that we can still read its ribs today, still trace the outline of an animal that lived in a world where nothing had yet thought to eat another animal. Before the arms race, before the throne existed, before any creature had to be fast, or armored, or terrifying, or anything other than alive. Every dynasty in the story that followed, every apex predator, every ocean ruler, every creature we have described tonight as dominant, inevitable, permanent, was, in the end, temporary. Not because they were weak, but because the ocean is patient in a way that no individual species can be. It has time that no dynasty can outlast. It has seen Anomalocaris replaced, Camarasaurus replaced, The sea scorpions replaced. Dunkleosteus replaced. Each one, in its time, the pinnacle of what evolution could build. The shark has held its place longer than any of them. Nearly 450 million years through catastrophes that remade the world. That is not nothing. That is, by any measure, one of the great achievements in the history of life on Earth. But the ocean was here before the shark. And if we are not careful, if we continue treating the ocean as a resource rather than as the oldest story on the planet, we may discover that it is very patient about finding replacements. The question that stays, after all of this, is not what came before the shark. That question has an answer, and it is extraordinary. The question that lingers is what Dickinsonia might represent, not as a fossil, not as a data point in the history of predation, but as a moment. A world without hunger, without pursuit, without the machinery of fear. We have no evidence that such a world can exist for long. Evolution found its way to predation quickly and has never entirely abandoned it. But it existed for perhaps 90 million years, longer than the age of dinosaurs. The ocean held creatures that simply lived without eating each other. That it ended is not a tragedy. That it happened at all is the strangest and most quietly astonishing fact in this entire story.